the set is of this form. No, some real number. A belongs to Rn, and this is fixed, and how would we find out if this is closed under scalar multiplication? So, what is this set actually? Maybe that needs to be clarified a little first. This is essentially, I should have written it slightly differently. Let me first clarify that. Okay. The set we are talking about is essentially this. Set of points x, okay, that belong to Rn such that A transpose x equals B. B is some fixed real number, An is some fixed vector from Rn. Okay. So, you take any point from Rn and then verify whether or not it satisfies this equation. If it satisfies, then it belongs to the set. If it does not satisfy, it does not belong to the set. One example could be, let's say we are talking about R2, set of all points so this is your A transpose, this is your B. Okay. If I chose A transpose to be this and B to be this, then this set will essentially be all values of x that satisfy this equation. Can you give me examples of some values of x that will actually be in this set if this is A transpose and this is B? 1 and 0, yes. 1, 0 will be there, and then, sorry, 0, 1. There are an infinite number of them. Okay, so all these points will belong here. But if I take, this will not belong to this set, because if you put x here, the x A transpose x will give me 2. That means this point from R2 does not belong in this set. Okay. So now you get an idea. So this set is a subspace of Rn. Okay, that's clear. Now the question is does this form a subspace, or does this form a vector space? How would you find out? Well, this is the idea, right? So you take any element from here, right? That means that element will satisfy this. You take that element, and if you do scalar multiplication, you scale that element by alpha, and you verify whether that scaled element satisfies this equation. If it does, that means it's closed under scalar multiplication. If it does not satisfy, then that means it's not closed under scalar multiplication. Is it clear? Okay, all right. Let's say we take x belongs to S, which means A transpose x equals B. Okay. If you say x belongs here, then I know that this is true. Okay. Now, if I do scalar multiplication, right, I want to know whether this belongs to this. It will belong to this if you take this vector and you do A transpose B. This has to give me B. If it does, then this is here. If it does not give me B, that means it is not in the set. That means it's not closed. If you take an element from this, scale it, it goes outside the set. Now the question is this true? It's not? It's not, right? Because this is an inner product. If you multiply one of the elements of the inner product by a scalar, at least in Rn, that element comes out, the scalar comes out. This will be alpha times A transpose X, but we already know A transpose X is B, right? That means what I get is alpha times B. That means this does not belong here. If I scale A transpose, the new scaled element gives me some other number, not B. So this is not closed. So you don't have to verify anything else. I mean, you can still verify what happens to vector addition, but scalar multiplication is not satisfied. That means it's not a vector space. But can you tell me if this is closed under vector addition? How will you verify if it's closed under vector addition? We know it's not a vector space, but we still want to know if it's closed under vector addition. Well, you take two elements. If you say it belongs to S, what do we know about these two elements? Well, if you say these two belong to S, we know that both of them satisfy this, because that's the definition of that is the condition for membership in the set. We know that A transpose X1 gives me B, and A transpose X2 gives me B. Now the question is, does this belong to this set? How will you verify? Well, you take this and you find this out and you see if it's equal to B. Is it equal to B? Well, it's not. This is distributive. So if you expand this out, you get A transpose X1 plus A transpose X2. Both of these are B. That means I get 2B. It means this is not closed. So in fact, this set is neither closed under vector addition nor under scalar multiplication. In fact, this set does not even have the zero element. Does this contain the zero element? Why not? Hey, no. The element is not B. So the element in the set is X, right? If the zero element was there, that means one of the elements here is 0, the 0 vector. If you put that here, A transpose 0 vector will give me 0. B is not 0. Well, I have not said anything, but let's assume I have said B is not 0. Then this is not, in fact, it won't have the 0 element. Okay. What if B was 0? Is that a vector space now? Is the 0 element in the set now? 0 element is there, no problem. But that does not mean it's a vector space. It can be a vector space. Sorry, it's not? I mean, just go through the same procedure and verify. Why will it give 0? Here, let's take this example, right? Let's say this is 0. If I put 0, of course I get 0. Are there other values of X that will give me 0? Here, they will, right? 1 minus 1, 2 minus 2, 3 minus 3, all of them will give me 0. So, now, all I've done here is I've set B to 0. Okay, and I'm asking you to verify again if this is a vector space or not. Is that clear? Okay. Is it closed under scalar multiplication or no? In fact, this example is exactly this, right? It's just that A transpose is now A1, A2, and then I should have said this is equal to 0. Yeah. Yeah. Okay. So it's there in the question, I forgot to write it there. Okay. Let's do C, and then we'll and the rest you can do. X transpose, set of all points such that X transpose X equals 1. Is it closed under scalar multiplication? Why not? What do you get? So if you take X that belongs to, and this is satisfied. Now if you scale that by alpha, for this to belong to this set, the transpose of this multiplied by this should be equal to 1, right? But it won't be. Okay. So this is not. Okay. In fact, in R2, what is this set in R2? If n was 2, X transpose X equals 1. What does it look like? The set of all points that satisfy this. Well, expand it out. If it's in R2, right, then you have x1, x2, x1, x2. This is X, this is X transpose. This will simply be at the circle of radius 1. Okay. These are the set of points. Now if I choose a point here, that's this vector. Okay. If I scale this vector by some alpha, it will always go outside the circle. That means it won't be in this set anymore. So it's not closed. Okay. All right. And then we'll do the fifth problem. That's clear. So there is a set of vectors and you're asked to find out if it's linearly independent. How will we find out if it's linearly independent? What is the definition for linear independence? Go back to the sheet. Yes. Yeah. What is the definition? Yes, if you take the linear combination of these, this should produce 0 vector. But what is the condition? Yes, all alpha i's should be 0. And that should be the only condition under which you get this is true. For any other non-zero alpha, this is not true. Is this linearly independent now? Okay, why? Right, if you in fact for any set of vectors, right, if all the alphas are 0, you will always get 0. But that should be the only condition under which you get 0. Okay. If there is any other possible values for alpha 1 to alpha 4, that is non-zero, and that still gives you the 0 vector, that means it's linearly dependent. See, if you do the summation, what do you get? If you compute this, right, what will be the vector that you get? It will be a vector that is in terms of alpha 1 to alpha 2, alpha 3, alpha 4. What will be the first element? The first element will simply be alpha 1 plus alpha 2 plus alpha 3 plus alpha 4. What about the second element? Okay, third element. No, the only thing that's left is everything else is 0. This one is 4. Now the question is, when will this be equal to? Are there non-zero values for alpha 1 to alpha 4 that will give me this? No? Okay. Well, we know one thing for sure, alpha 3 has to be 0, right? Okay. If alpha 3 is 0, we know that alpha 4 has to be 0. If these two are 0, alpha 2 is 0. If these three are 0, this has to be 0. So the only possible values for which the left hand side will be equal to the right hand side if all the alphas are 0. Okay. So this set is in fact now linearly independent. Okay. If I had changed the first one to 0, right? If I had changed the first vector so that the first vector is now the 0 vector, this will now become this. Now is this set linearly independent? Well, alpha 2 to alpha 3 have to still be 0. Well, then at least from this equation, they have to be 0. But alpha 1 can be anything we want. Okay? Which means now you have a set of alphas where all of them are not 0 and you can still produce a 0 vector. That means that's a linearly dependent set. Or if I had changed it like this, now you can we'll have to rewrite the first equation and the second equation. What will be the first equation now? Alpha 1 plus alpha 2, 3, 4. Two plus alpha 3 plus 2 alpha 4. Now what do we do? Well, these two are still left untouched. That means alpha 3 has to be 0, alpha 4 has to be 0. If that is the case, then these two disappear and all we are left with is minus alpha 1 plus alpha 2 equals 0. Can we say anything about alpha 1 and alpha 2? Well, obviously if both are 0, this will be 0. But are there non-zero values for alpha 1 and alpha 2 that will give me, which will satisfy both these equations? Yes, when alpha 1 equals alpha 2, then all those values will satisfy both of them. That means this is now not linearly independent. And you can already see that because this vector is a scaled version of this. Okay? All right. Okay. That's all I wanted to do for the first tutorial.